Hello, this is a project video for the cybersecurity course EC521 at Boston University. The scope of this project is machine learning for malware packet analysis. The aim of this project is to create a model to detect malware by looking at the network traffic information. The architecture of our project consists of 4 components. First is data collection. This involves collecting PCAP files from machines infected by different types of malware. Second, we do feature extraction. We parse the PCAPs and extract the relevant features about the malware and label the data. Third, we do training. This involves training our models with the labeled features. And fourth, and finally, we do testing. We then put unlabeled testing data and ask the models to label which malware it thinks the testing data comes from. We targeted malwares that generated a significant amount of network traffic. For our purpose, we chose Zeus Game Over, Conficker, and Drydex. Zeus Game Over is a botnet made with the components of the Zeus Trojan, a Microsoft Windows botnet used for bank fraud and distribution of CryptoLocker. It uses encrypted P2P and DGA to communicate. Conficker is a Microsoft Windows worm that allows the attacker to upload and execute binaries on infected systems. It uses the UPnP protocol and RPC service to propagate in a network. Drydex is a Microsoft Windows Trojan for stealing bank information. It communicates with CNC and other peer nodes through P2P protocols. For feature extraction, we divide each malware PCAP into sessions, where each session represents a single network connection, and so each session obviously consists of multiple packets corresponding to the same network connection. From each individual session, we extract the following features: the source IP, the destination IP, the source port, the destination port, and the min hash of the session. You might be wondering what a min hash is. A min hash is a type of locality-sensitive hash. Simply put, what this means is that similar payloads should result in similar hashes. For our training phase, we used 2 different types of models. The first model we used was a single-layer perceptron, or in other words, a neural net. Our neural net model had the following architecture. At the input layer, we accepted approximately 50,000 samples, where each sample had 133 different values. We had a single hidden layer, whose activation function was the sigmoid function, and it contained 3,000 neurons. At the output layer, we had 4 different classes whose activation function was also sigmoid. The second model we used was a convolutional neural network, which had the following architecture. The model accepted a matrix with dimensions 20 by 133. Within the model, we used a single convolution layer that produced 64 different feature matrices with a kernel whose dimensions were 2 by 2 and had a stride of 1 by 1. After the convolution layer, we used a max pooling layer in our model whose filter dimensions were 2 by 2 and whose strides were also 2 by 2. In our fully connected layer, we had 1,000 neurons, which used the sigmoid activation function. This layer then outputted to the output layer, which also used the sigmoid activation function and output 4 different classes. As you can see, for training, we use the following PCAP files. If we open up Wireshark, we can see what one of these PCAP files looks like. After we have trained on this data, we save the weights that were generated by our model. We then use those weights to test our model's results on a test data set. Our test data sets included approximately the same amount of data from the 4 aforementioned malware. The demo.py script first loads in the data using the getFormatedData method. We then use the loadWeightsPredict method to create the model we are going to use for testing and load in the weights from our training model. Now let's run our demo.py script. After running this model, we can see that the model successfully classifies our samples 84% of the time. This result adds validity to our hypothesis that we can use machine learning techniques for intrusion detection on networks. This being said, there is still a lot of work that needs to be done to make the model truly general. We will need to collect more data so that the neural networks can produce better representations of the features within the model.